Okay, now we go on to the other types of diagrams that we have to deal with. And what we have said now is that to get two independent properties, I can have either V, H, S or U. We can have any of these properties, V, U, H and S. Any two of these are always two independent properties, no problems. P or T and any of these are always two independent properties, no problem. But in saturated state, it has to be either any two of these or pressure and any one of these or temperature and any one of these or any of these with X. So X with any of these properties P, T, U, V, H, S, this will constitute two independent properties. And when we do problems, we get different combinations of properties coming in. We should not get some extent. We just simply ask the question, do we have a saturated state? If yes, then we have to look at all of this. If no, any two of these properties are good enough. If the state is completely defined, it may be a little more difficult to get properties. If say you are given U and H are given, we automatically know that I have two independent properties. The only trick is how do I get S, P and T? And this is a little more tricky. A good software package will get is no issue at all. You just put these numbers and tell you what it is. Okay, so that will give us the complete details about states of all these vapor, liquid and mixture states. Now we look at some other properties, property diagrams, beginning with the pressure and specific enthalpy diagram, the pH diagram. This diagram is very popular with users in refrigeration, air conditioning and those type of cycles. And by looking at the diagram itself, people used to solve problems in the good old days, but 25, 30 years back. Today, of course, you can do all of that on a computer or even program it. But one needs to understand what is the diagram telling us and how do I know that I'm doing the right thing, and in case I did a mistake, how do I correct it? So I'll briefly describe what is the appearance of this diagram, what are the different regions on this diagram, then I'll show you some real pH diagrams, and then we'll see pH diagrams for many other substances. So the y-axis on the pH diagram we have P, and on the x-axis we have specific enthalpy H. And if we do the same thing what we did earlier, that is we plot all the saturated liquid states, then we will get a bunch of states which are something like this. So this is all X equal to 0. So what we have done is we have taken this pressure and asked what is at this point, it is this pressure, and at that pressure what is HF. So we have plotted P versus HF. That's all we have done, nothing else. And now we do the same thing with P versus Hg, the saturated vapor state. And this graph will give us a bunch of states that have approximately this shape. And this is all X equal to 1. And what we have plotted is pressure versus the dry specific enthalpy in the dry saturated state, Hg. And the critical point is right at the top of this, the critical pressure. And this graph will of course always end on the lowest point, it will be the triple point. So except water, for most substances we don't get anywhere close to the point where we start seeing solid, except maybe carbon dioxide in that case. And so in many diagrams, the triple point line and what happens at the bottom is not even shown. But it is there, we don't need to be too concerned about it. So if you draw these lines, we get this shape. One on that side and one that comes something like this. So this has this particular shape coming in. inside this region, and we will now start giving it a name, because this is what all diagrams will look like. This we will call as the dome, or in many cases, this is the saturation dome. So we'll use this word very frequently, that the state lies inside the dome is the wet state, which means that the state is somewhere in this region inside here. So that's inside this is all our wet saturated states. X equal to 0 is here, X equal to 1 is there, and at constant pressure, if you keep heating it, you will go like that from X equal to 0 equal to X equal to 1. Constant temperature lines will go something like this, then they will continue like this, and then start going down there. So this is T1, and like that there will be a similar line T2, and then in the critical isotherm there will be a line T3. So this is what one sees. So this is T2, and like that there will be a family of these lines coming on this. And along with that, we can also plot constant entropy lines. So that was T, and constant entropy lines on this line diagram, they end up going something like that. S1, S2, and so on. So what does this diagram tell us? This side is the compressed liquid, this portion here, or the subcooled liquid. This side here is superheated vapor, and above this is supercritical fluid. Or dense fluid, either way. And the nice thing about this is that processes like heating and cooling especially in a flow process. And an example of that is, say, the air conditioner evaporator in which we are pumping in the substance, it goes through all the tubes, comes out. In the real case, there will be some pressure drop. So the outlet pressure will be slightly less than the inlet pressure. For the time being, let's not worry about it and say that there is no pressure drop. In the first cut analysis in thermodynamics, we assume that flow processes involving heating and cooling and no work transfer, these are constant pressure processes or isobaric. That's an important assumption we'll make in this course, that wherever we are going to look at a flow system and we look at either condensation or heating or cooling, we say that it is isobaric, which is an approximation to the extent that we are neglecting pressure drop in the pipe. Pressure drop is what one would have learned in a fluid mechanics course, the same thing. It's a good first assumption. When you start doing real systems, then of course you will start worrying about pressure drops, but they can also be shown on this diagram. So let's ask the question, what happens in the condenser of your air conditioner? Well, we start with a superheated state, say somewhere there, which is what we got after the compressor. And then we put it into a set of tubes on which we blow ambient air. The temperature of the vapor inside is more than the ambient temperature, so it starts rejecting heat and it gradually keeps cooling down, and it goes through all these states like this. At some point it becomes a saturated vapor. We continue cooling it, and at some point we say, okay, enough cooling is done, and this is our exit state. So this line, this 1 to 2, is your ideal condensation process in the air conditioner. What the real process will do, there will be some pressure drop along this line, so the final state will be at a pressure slightly below this pressure. So we can say that it came somewhere there, and so this line would be somewhat off from here. That's how we show a state on these state diagrams, and we show a line with an arrow to depict what is the process. A solid line means that this is a reversible process. If the process is irreversible, this will have to be a dotted line. And the nice thing about this diagram is that if we are able to get these two states plotted on this diagram, then we can say, well, what is the enthalpy change in this process? Well, if you do the mass conservation and first law analysis, you'll get a relation that heat transfer rate is the mass flow rate multiplied by the enthalpy difference between the inlet and the exit states. That is quite nice because you can just go down this chart, look up this value of the specific enthalpy, go down this point, look up this value of the specific enthalpy. We can get H1, we can get H2, and the difference of this is the enthalpy drop during the process. That multiplied by the mass flow rate is the heat transfer in this process in steady state, no change in kinetic and potential assumptions. So that's a nice thing to know. The next thing that happens in the refrigerator, and we can now see yet another process that happens there, is throttling. In the previous module, I discussed that if potential energy changes are very small, kinetic energy changes are small, it is adiabatic, no work transfer, steady state, then inlet and outlet enthalpies are equal to one another in a throttling process. So in this diagram, H equal to constant will be a vertical line, and that's what we do in a fridge or an AC, that after this thing, the fluid is throttled and brought down to a low pressure. And this process will be shown by a broken line because throttling, no matter what, is a hugely irreversible process always. So this brings us to another state, state 3, and it tells you that, okay, if we know the specific enthalpy at 2 and the final pressure of throttling, then I know that H3 is equal to H2 because it's the isenthalpic process. P3 is given to me. I have two independent properties, we can do the rest of the calculation. It is at this state that the refrigerant enters the evaporator where the cooling takes place and keeps getting heated up, and it goes through a bunch of in the room, and the wet saturated refrigerant kept getting heated, its dryness fraction kept increasing, became X equal to 1, and then became a superheated vapor. That's what was happening. And to complete this refrigeration cycle, we say at this point it enters the compressor, and if we assume that the compression process is reversible adiabatic, it means that it is an isentropic process, then the process inside the compressor will go along an constant entropy line. This will again have to be a solid line, and that is our compression process. And so very nicely, we are able to visualize what this diagram looks like. And also, we can even get quantifiable data. Earlier, we had to look up the charts and do interpolations. These days, we can even make this whole thing in a software, and by touching the points on the screen, we can just get all the data from there. Or to be more exact, we go to the tables, input all these properties, and get much more accurate data. That is the best thing to do. So that is the pH diagram. Now I'll show you a real pH diagram. Okay, the first one that I have here with me is pH for water. And there are lots of lines over there. But what we have to see mainly is that pressure is on this axis, a logarithmic scale in megapascal. On the x-axis, it is specific enthalpy in kilojoules per kg. And you can see these dark lines, it says saturated liquid line, here it goes up. And on this side, it says saturated vapor line, this goes up over there. And at the top is the critical point for water. And from this, you can see there are many other lines on this. So let's spend a few minutes trying to figure out what they tell us. The first is a set of lines that you can see here. It says 0.1, 0.2, 0.3, 0.4, and 0.9. And here it says x is equal to 0.5. So these lines inside the dome are lines of constant dryness fraction. There is another set of lines which are going here, slightly at a larger angle than that. S is equal to 5 kilojoules per kg Kelvin. So these are lines you can see here everywhere. This is S is equal to 8 kilojoules per kg, 9.5, 8.5. These are constant entropies lines. H, constant S lines, constant X lines. Now X lines of course are inside the dome only, they are not outside the dome. Then you can see these are the lines which are going constant specific volume lines. So these are those lines. 5 meter cube per kg, 0.03 meter cube per kg, and so on. And these funny looking lines coming from the top, these are constant temperature lines. And what I was just drawing are these lines over here, which says like 550. So this is the line that is coming at 550. This is the line coming at 500. This is the line going at 450. So they're almost vertical lines. In the compressed liquid part, become horizontal inside it, so they have not been shown, but we know that it is the same thing. And then from there, it further goes down and comes 500, 450, 400, 350 Kelvin. So on that phase diagram, this is what we were looking at. We have constant temperature lines, we have constant entropy lines, and we also saw inside the dome constant dryness fraction lines. And of course, we are also, I haven't drawn here, but also constant specific volume lines. So that is for water. And another substance that I'll put up here is oxygen. Simply because now the scale of temperatures is completely different on this. But you can look at the shape of this, it's exactly the same. Okay, so here we are. Pressure in megapascals, 0.1 megapascal, 1 megapascal, 10 megapascal. Specific enthalpy, H. And same thing we see here, saturated liquid line over there, saturated vapor line over there, just like what we had seen qualitatively there. So this is your saturated vapor line, and on the other side we end up getting the saturated liquid line. Inside the dome we have the similar things, 0.1, 0.2 like this. This is constant dryness fraction over there. Then 1.5, 1.75, these are all constant specific entropy lines. Outside these are constant specific volume lines over there. This is S equal to 3 kilojoules per kg K. And then we have constant temperature lines, which is like what we have drawn there. This is a constant temperature line and the constant temperature line. The temperatures here are very low, 150 Kelvin, 135 Kelvin, 120 Kelvin, 105 Kelvin. We are looking at very low temperatures. But look at this thing here. Ambient pressure is 0.1 megapascal, and so it comes over here. So at 0.1 megapascal, what we see is oxygen in this condition is in a wet state, which means that at this thing, if we cool it down, and this temperature here is 105 Kelvin, this is even below that, it turns out to be about 77 Kelvin. So 77 Kelvin, 100 Kelvin at these pressures, oxygen behaves like has a liquid and a vapor state, and you can start getting wet states in this. And the reason for saying this is that in the cryogenic engines, picture of which I showed you yesterday, the oxidant is liquid oxygen, which is filled at this state. So we need to know what is the specific volume there, how sensitive is it to temperature, what is the specific entropy, what is the pressure and temperature to which I need to cool it, and then we know how much is the volume that we need to have in the solid rocket motor to put that much liquid oxygen in it. There are many other uses of oxygen. For example, a medical oxygen cylinder that comes filled at 150 bar. 150 bar is 15 megapascal, which is somewhere here. And if you say what is ambient temperature, that's about 300 Kelvin. So it is 300 Kelvin line is here. So a medical oxygen cylinder is at this state here. Highly superheated vapor, but substantially high pressure. So we need to think, is this compression going to deviate the behavior from what we are seeing here? Okay, so this is for oxygen. And now we'll see for a few more substances and see one important aspect. Same thing what we have seen so far. Specific enthalpy on the x-axis, pressure on the y-axis, the logarithmic scale. But what I've done here, and this is data taken from the tables and I just made the plot myself, is this side, this is the chart for water. On the left side are saturated liquid states for water. On the right side, sorry, this is not water, this is ammonia. This is for ammonia, and on the right side is dry saturated vapor state of ammonia. And then we have put other things here. So this side is, you have propane, and then we have R12 and R22 over there. So what we are seeing here is they all have the same shape, but in making this drawing, we have to be very, very careful because in all these cases, specific enthalpy, which is here set to 0, is decided quite generally as per the wishes of the person making the property tables. In these materials, the specific enthalpy HF at 200 Kelvin has been set to 0. And so we could make all these property plots of different substances on this. Water tables that you see, there the specific enthalpy of saturated liquid water at triple point is set to 0. So I cannot just make that plot and plot H of that on this. They will look fine, okay, but actually they are quite different there. The whole thing will have to be shifted quite a ways out. The other thing that this sort of a picture tells us is that what are the substances that have somewhat similar properties. And this issue came up 20 years back when R12 as a refrigerant was banned because of ozone layer depletion. An immediate question people started asking that what is the material that I can put in my refrigerator and air conditioners. So people started looking at these properties and said, look, let's see what all materials we have. We have propane, we have butane, we have R22, 23, 14, so many hydrofluorocarbons. And we start looking at all the properties and we find that two materials which are very similar in properties, we can substitute them with one another provided all the other things don't come in the way. For example, there's no corrosion or reaction with the oils or it becomes toxic, then we won't use it. But if those things are also okay, then what it means is that you can take the existing refrigerator or the existing air conditioner, throw out R12 and put it your new refrigerant, and your fridge and AC is good enough to keep working on. And that's what initially was done. But as time goes on, we came from R12 to 22. Now 22 has to be banned and removed. So we are now looking at even more refrigerants which we can change. And that's how you see in the market today 134A in refrigerators. 5 years from now, even that will be probably phased out and you will have something more coming in. And this is the basic starting point from which we do the design and engineering of all those devices. So that's why I put this diagram, and the idea is that beyond just looking at it and getting properties, it tells us a lot more about how these substances behave and which can be used in lieu of the other ones.